Hello, this is Mr. Humbard here. I'm going to be recording this video about 3.2 and 3.4 equations and the derivation for those as well. This is all with constant acceleration, so let's get started. So for these equations, this is covering that equation sheet and the math involved to rearrange some of those. Let's derive them all first, and I'm going to do 4 videos, I think, one for each row. That way we have plenty of material. So to start, I will do the first one, the velocity time equation with no distance given. Velocity time, no distance. Exactly like so. Alright, now let's write out what we know about an equation of a line real quick. So that's going to help us a bunch with this. So an equation of a line, we know that it usually has some axis with the y going up and the x going in the y vertical, x horizontal. It has some line that's straight usually. If we want the equation of this line, we want the intersect, where it intersects the y-axis, usually called b. That's the distance up from 0, or the origin. That distance is b. And then we want the distance up to y, that distance from the origin, that is the y. And of course we want or know the equation of a line, y equals mx plus b, where m is a slope and b is the y-intercept, and y is your output, x is your input. For every x you plug in, you have some function of x as an output for y. Alright? So, now, knowing that, let's solve this equation for m minus b, y minus b equals mx. Divide all this by x. Nicely, that's going to cancel, and we get m equals the rise over the run, and the run's going to be from 0 to some x value over here, and the rise is going to be from this b value to this y value. So we want to subtract that. So it makes sense, because that's going to be our slope. So y value minus b value over some x value. Right? That's our slope of the line. Let's do something similar now with velocity versus time, and that's how we're going to derive this. So to start, let's draw another graph. We will draw this upward, same as before. This time around, let's use a v and t, and this is going to be our y, this is going to be our x. So let's write out everything we know. This is going to be some v initial here, and we're going to write out our equation. We'll say up here is our v final at the very top, and v initial is where we start. And we want to write everything out like the y equals mx plus b. So we'll do that. So v final equals sum m, we don't know what that is yet, times our x, which is at t this time, plus v initial. So that's our equation. And we can solve this, same thing we did before, for m. We'll get some rise over run. So vf minus vi equals mt divided by t, both sides. We're going to get the definition of acceleration, in fact. Because acceleration is some change in velocity over some time period, which is what we have. So m here is acceleration, which is some change in velocity over a time period. And that is our first equation. That delta stands for change, of course. Final minus initial. Now, let's go and solve this for our other forms. And notice that this is with no distance given, so a equals vf minus vi over t. If I want to get t by itself, I multiply by t over a. Nicely, a will cancel here, and t will cancel here. I'll get t equals vf minus vi over a. So there's our second one. Let's get some more. Two more. So from this, instead of dividing that out, we can just multiply by t here instead of dividing by a, and get a times t equals vf minus vi. And then we can add vi, and we'll get vf, because vi will cancel out nicely. So we'll write that here. And I'll get vf equals at plus vi. That's our next one. And we have one more. All we have to do is subtract at both sides from this equation. And it looks like I'll get what vi is. Okay, so now vi is vf minus at, if I could write that, right? And I'll box this one too. So those are our four forms. That's how we got those. And that's it for part one.